In this video, we're going to investigate the different terms from the kinematic frontogenesis equation in one dimension to illustrate how we can change the magnitude of our temperature gradient by these kinematic processes. I've started here with us having rewritten out the kinematic frontogenesis equation in one dimension with our four different terms of confluence, shear, tilting, and diabatic. And so let's begin investigating this kinematic frontogenesis equation with our kind of schematic diagram here, looking at confluence. And so ultimately, we want to look at our confluence term. And so what does it mean to have confluent flow? Confluent flow might look something like this. Air coming together. So if we were to draw then what would happen at some later time, since that's ultimately what we're trying to figure out here with our frontogenesis, is how is our pattern changing with time? So now we're at t equals t naught plus delta t, if this was t equals t naught. What do you think would happen to our lines of potential temperature? That's right, they would move closer together, because basically what we're getting is cold air advection on the cold side and warm air advection on the warm side, such that we would not change the location of our center potential temperature line, but the one from our south would effectively move north, and the one from our north would effectively move south. And so in this situation, this process would be a frontogenetic process because we have increased the strength of our temperature gradient, right? The magnitude of our temperature gradient here, same change in temperature, but over a much smaller distance, such that this is frontogenetic. If we were to reverse this process and have difluent flow, what do you think would happen? Correct. In difluent flow, we would have our air moving out such that it would weaken our temperature gradient, such that that would be a frontolytic process. So that's it for confluence. Let's think about shear. Our shear term is the term where we have du dy times d theta dx. And so thinking about our gradient in theta here, what is our gradient in the x direction? That's right, it's 0. And so in this way, when we're in this one dimension, we wouldn't be able to generate any strengthening temperature gradient in the y direction, given our current setup. Now, if we were looking at our gradients in an x direction, we would be able to generate then temperature gradients in our y, and so that's what we're going to look at here. And so specifically, we're going to look at this shearing deformation term. And we're going to do so by now considering a temperature gradient in the x direction alone. And so we're going to draw a couple of isentropes here. Such that we have theta plus delta theta, theta minus delta theta, and theta minus 2 delta theta. So we have essentially what is warm air to the left, cold air to the right, and now let's assume some shear in the flow, right, due to this shearing deformation. And so right in the middle here is where we would have our winds going in opposite directions, such that that is where our shear is, getting stronger then as we moved away. And so let's just think about how this might then change this flow. So again, here we only have our gradient in the x direction. But that what we're essentially going to do is generate this and put some of this temperature gradient that's only in the x direction into the y direction. And so here we're going to have d theta dx as less than 0. Right, because our temperature is getting colder as we go in the positive x direction. And here in this case, du dy is also less than 0 because it is becoming more negative as we go in the positive y direction. And so if we have that as the case, du dy is less than 0 and d theta dx is less than 0, then our overall term is these two things combined. And so if we have a less than 0 term times a less than 0 term, we end up getting a greater than 0 term, such that we're going to generate temperature gradient in the y direction. And so what's going to happen is we are going to push our temperature gradient on the north side to the west, to the south side, to the east, such that that shear is going to generate then a pattern that may look something like this. Oops, let's change this to red. Right, so more northerly lines. Such that if we kind of draw this zone here, we've created stronger temperature gradient right in that zone. And again here, this is now our theta plus delta theta, our theta minus delta theta. And so we can see we've now generated in our y direction some amount of temperature gradient. And so that's the shearing deformation. We can generate new temperature gradients in a different direction because of the shear in the flow. Now let's think about our tilting term. Our tilting term here, we want to think about now, instead of a horizontal look, a look in our y, z or y, p minus p direction here. And so again, our fronts aren't just at one level. We have a tilt to our temperature gradient and our fronts, and we always tilt back towards the cold air. So we have theta, theta minus delta theta, and theta plus delta theta. And so again, this might be at our time t equals t naught, and we are looking to figure out, well, what's going to happen at some later time. So if we go ahead and draw again our y minus p axis here, now at t equals t naught plus delta t, we want to know what is going to be the effect of, say, an indirect circulation and a direct circulation. And so let's go ahead first and figure out what would be an indirect circulation. And so we must recall what happens in cold and warm air in terms of a indirect circulation. Indirect means it's basically not the normal circulation. And so in this case, that would mean cold air, which we have here, is going to rise, and our warm air is going to sink. This would be our indirect circulation. And so thinking about what's going to happen to this temperature gradient, what is going to happen? How is the tilt of these isentropes going to change? And so when we know that cold air rises, right, that cold air is going to further expand and cool adiabatically. And then the warming air will sink and compress and warm adiabatically, such that we are going to get more vertically oriented isentropes. So there's maybe theta, theta minus delta theta, and theta plus delta theta. Now, I did not do a good job of drawing these the same, so we're going to quickly redo that. Trying to keep the same spacing as we had before. So there's maybe theta. There's theta minus delta theta. And theta plus delta theta. And so the thing we want to remark here is that we want to look at the difference in how far is this delta y in these two scenarios. And so it turns out that when we tilted, right, we are now projecting over a smaller area, such that we are getting a more direct gradient in our y direction, such that an indirect circulation is frontogenetic. This would be similar to what we see in jet streaks. If we reverse this, if we had a direct circulation, we might see an even more dramatic effect. And so let's quickly draw that out. Here again is our y minus p, our initial theta, theta minus delta theta, theta plus delta theta, at our time t equals t naught. And now we're going to think about our direct circulation here. Such that our direct circulation is going to have warm air rising, cold air sinking, and how is that going to affect our temperature gradients? And so we might see that our theta looks something like that. Theta minus delta theta, theta plus delta theta. Such that now if we look at our change in y here, we would see that it is much different and that our direct circulation is frontolytic. We are going to decrease the temperature gradient as the result of a direct circulation. One more term to go here, our diabatic term. Here it's not, it is again changing with time, but now it's changes in diabatic heating over our basically y direction. So we could look at a situation that looks something like this. Here's our ground. And now we're going to again be looking at a cross-section. And our cross-section may have some sort of frontal zone. Remember, frontal zones, areas of increased static stability, so lines of potential temperature close together, such that we have our cold air here to the west, our warm air to the east. And again, these are theta lines, such that we have, theta, theta minus delta theta, and so on. And so now the question is, diabatic processes, what are we really talking about? Well, we're talking maybe about the sun. And where do we see clouds? And so let's assume our clouds are over the cold region. And so thinking about when the sun is out, what's going to happen, right? We have the sun's rays coming in, warming the warm side. Then they're going to come in and be partially absorbed by the clouds. And so we need to ask ourselves, what is going to happen to the strength of our warm front as a result? So both sides are still going to warm a little bit, right? So the cold side will warm a little, but the warm side could warm a lot, such that this setup is frontogenetic. Right? By warming the warm side more than we're warming the cold side, we are going to increase the strength of this temperature gradient through time, such that this diabatic process would be frontogenetic. Now, given this same scenario, but it being nighttime, what would happen? Would this be still frontogenetic? At nighttime, then, without clouds on the warm side, we would allow lots of cooling. And on the cold side, with our clouds, there would be less cooling. Again, both sides would cool, but the warm side would cool more, and the cold side would cool less, such that this would be a frontolytic process. We would decrease the strength of our front. Again, we could change where the clouds were, and that could also change the impact of where we're going to have frontogenic or frontolytic. And so let's go ahead and draw out that scenario of changing where our clouds might be. So again, here we have our frontal zone, increased static stability. But now we're going to place our clouds over the warm sector. And so again, if we have our sun, Mr. Golden Sun, please shine down on me. We are going to warm our cold side more than we're going to warm the warm side, such that this whole process is frontolytic. And that's it. Those are our four terms and how they can impact the strengthening or weakening of our fronts from this idea of the magnitude of our potential temperature gradient. Thanks for watching.